Hi everyone, today I will be walking you through Lab 4 of Physics 2212, titled Circuits and Capacitors. The purpose of this lab is to understand the effects of resistors in series and parallel. We will use multimeters to measure potential differences and conventional current. Finally, we will model the behavior of capacitors and ohmic resistors. The physics principles at play in this lab are Ohm's law, which equates voltage with current times resistance, capacitance, which equals the quotient of charge and voltage, the node rule, stating that current flowing in equals current flowing out, and the loop rule, requiring that the total potential difference around the entire circuit equals zero. Part 1 of this lab involves creating a circuit in PHYS Circuit Constructor Kit. Let's first construct a circuit using two 1.5 volt batteries, a 47 ohm resistor, a 100 ohm resistor, and two ammeters, as seen to the right. Given the initial circuit, we can predict the current by dividing voltage by resistance, per Ohm's law. Our predicted current is 0.0204 ohms. The actual current is just as we expected, though with less precision. If we were to reverse an ammeter, the reading would flip sides, since the current would flow through the ammeter in reverse. Now, let's replace the second ammeter with a voltmeter. We expect the reading to be 3 volts, since there is a 3 volt potential at the battery and a 0 volt potential at the resistor. In other words, this is the case because the circuit is open. The actual reading is 3 volts, as we expect. In the simulation, the voltmeter has infinite resistance, which creates an open circuit as no current can flow through the voltmeter. Now, let's go around the circuit and measure the potential differences from component to component. 8 checkpoints are marked to the right, and the measured potential differences between these checkpoints are posted to the left. To find the potential differences for the round trip, let's take the sum of our measured values. Notice that the sum is 0, which supports the loop rule, as energy is conserved. This is also supported by the chart to the right, plotting voltage across the circuit, where the starting and ending points meet at 0. Now, let's place an ammeter in parallel to the 100 ohm resistor. When doing this, the current actually increases from 0.02 amps to 0.06 amps. This is because due to the parallel ammeter, less current encounters the 100 ohm resistor. Given Ohm's law, V equals IR, since resistance decreases, current increases. Considering the node rule, this means that current increases everywhere throughout the circuit, as seen in both ammeters. Let's calculate the resistance of the circuit's components and compare them with the real values. Once again, using Ohm's law, we can find resistance by dividing voltage by current. The 47 ohm resistor was calculated to have 48 ohms of resistance, and the 100 ohm resistor 102 ohms of resistance. All other components have no resistance, as they have a net zero potential difference. The calculated resistance is higher than expected due to the lack of precision in the ammeter, as discussed earlier. For part 2 of this lab, let's create the RC circuit shown to the right using a 9 volt battery, a 200 millifarad capacitor, a 10 ohm bulb, and a 20 ohm bulb. When the capacitor is charging, there is a maximum current at first, but this current decreases exponentially with time. When the capacitor is fully charged, there is no current flowing. With a 10 ohm bulb, the capacitor charged in 10.2 seconds, and with a 20 ohm bulb, 19.5 seconds. This seems reasonable given that the 20 ohm bulb has twice the resistance of the 10 ohm bulb. When the battery is removed and the capacitor is discharging, the magnitude of current operates the same as when charging, but flows in the opposite direction. With a 10 ohm bulb, the capacitor discharged in 13.9 seconds, and with a 20 ohm bulb, 27.6 seconds. Now, let's determine the time constant of the capacitor in our circuit. Looking at the given equation under the title, voltage decays exponentially with time. We can take the natural log of both sides to remove RC, the time constant, from the exponent. To find RC, we need to plot the natural log of voltage over initial voltage as a function of time. The slope of this line will equal -1 over RC, so we can take the negative reciprocal to find the time constant itself, 7.04 seconds. To reflect on this lab, let's ask, what if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? What's the difference about a real ammeter, and how would it have affected the circuits you hooked it up to? A real ammeter does indeed have resistance, which means real life readings are to be less than true. Also, what if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Ideally, the capacitor would be charged instantaneously. However, in real life, all components have resistance, so time is indeed required to charge the capacitor. Thank you for listening, and I'll be back for Lab 5.